this class, as you know, is divided in two parts. First part, and I will be in charge, will be mainly discussing membrane operations. Why we have an important technology that we call membrane engineering is mainly related to the fact that we have many operations, separation process, molecular separations, chemical transformation, membrane reactors, and other products we call membrane contactors, which means all the process where we can control mass transfer, energy transfer between different phases. Very familiar to chemical engineers. Membrane distillation, crystallization, emulsification, condensation, all these basic unit operation of process engineering can be today realized using membranes. So we will discuss basically in this first part about these operations. There will be a second part, and Professor Yomoli will take care of this here, on how we prepare membranes. So we will start today with trying to justify why membrane engineering is important and why today all around the world we have similar classes to speed up the education at the graduate level, particularly in this area. So I will try to justify and give you an example where membranes are already very well established and eventually where membranes will be established in the very near future. All this activity is under the umbrella of what we call process intensification, which is related to the problem, familiar to most of you, of trying to have a continuous industrial growth that we call sustainable. That means that what we are doing for producing more and better has to be also something that does not affect in negative our future. Not on short time eventually, but on long time. So we have to leave to the new generation a kind of environment of better quality, or at least similar to the one that in which we are living today. For doing this, how to give an answer to a industrial sustainable growth, the best answer that we have today is what we call process intensification. If you want to know more about process intensification, you can read this first report of what is called a study in progress in Europe, sponsored by European Union and from some government, Dutch government, mainly the Netherlands, on what we call how to redesign, you see here, the sustainable world in the 2050, about 40 years from now, in the future. And a group of about 30, 35 senior professors, most of them in chemical engineers, are working on this kind of problem. How we can predict what will be in the future, the industrial world, and if it will be possible to realize a sustainable growth or not. And if you read this is the first report already published and is public. I will send you a copy eventually. I think we have here in the computer, so we will send you a copy. If you don't receive, let us know and we will send one. You will see that not only membrane engineering, but a significant role for this solving this problem is related to membrane engineering. A lot of examples on membrane engineering are predicted to be effective for realizing the sustainable industrial growth. So that is one of the problems that we have. Now, if you analyze carefully what do we mean for process intensification, you will see that in next discussion we will have, basically all basic properties of the different membrane operation that we will discuss are quite consistent with the principle of process intensification. That's why we have to understand more and to realize as much as possible and very quickly the basic principle of membrane engineering, which are consistent with the process intensification strategy. Not all the work can be done using membranes, but the integration of membrane operation, new membrane operation sometimes, with some other technology or other existing or also new other technology is at the moment the best answer that we have for realizing what our goal. Now, process intensification strategy means that in process engineering, that means in all the molecular separation, remember, is about 80% of the cost of any process is very much related to separations. So if you improve and if you realize appropriate separation system, you have an impact quite significant on most part of the operation or chemical transformation, mass and energy transfer that we have in our industrial world. So molecular separation is a very important aspect of all this story. Anyway, what we mean for PI, process intensification, is to realize new operation, separation, chemical transformation, contactors, characterized by much less energy consumption and much less raw materials consumption, if possible. But lower cost, much more safe, security is a very important aspect, and very quickly for arriving to industrial application, very quickly arrival to the market. In the meantime, we have to increase for this process the efficiency, the footprints, some new aspects. One time we were only talking in terms of cost about energy or labor cost. Today, for example, footprints, space that you are utilizing for realizing your process is becoming very important. We don't have any more space available in most parts of the world. So we have to try to have industrial production with relatively small footprints. Low emissions is related to environmental, eco-environmental phenomena, and other new aspects, automatization, remote control, etc., are becoming very important. They were not important at all 50 or 60 years ago. These problems were not existing. Today, automatization, remote control, all these information technology and advanced control system are part of the strategy of process intensification. So some traditional aspects are still present as energy cost or general low cost, but not only the traditional one. New problems are present. That means a new kind of technology has to be invented or realized. The basic principle of process intensification, how to realize what we were discussing before, are not so easy. Cannot be just obtain this final effect, just making a small plant, for example, small footprint, etc. It's much more than this. And for example, the principal objective that we have to realize, the basic principle of PI is, for example, to maximize effectiveness of intra and intermolecular events. So all the transformation has to be realized in a very efficient way. And that will avoid some side effect, negative phenomena, unexpected reaction, etc. We have to try to give to each molecule that is going through transformation or separation the same processing experience to obtain a uniform transformation. We have to optimize driving force at every scale, nanoscale, mesoscale, macroscale, and maximize specific surface area to which these forces are applied. This is directly related to the problem of transport across interface. Thin interface is the best way to try to realize this principle. And for us, thin interface is just membranes. So this direct relationship to the introduction to the membrane problems. We have to maximize all the synergic effect from different for partial process. Each chemical transformation, is industrial process is related to many different steps. We have to find a way to integrate and to have good positive synergic effect between all the different steps of the overall system. If you're able to do this, it will be possible to realize some of the aspects of PI. For example, we can have the control of partial orientation and energy in the molecular collision. We have to try to have a special uniformity, so not unwanted gradients, phenomena of hot spots of negative side reaction, and we have to integrate different function in the same process. So if you read this, you understand that it's not easy to realize this basic objective. So to realize the process intensification strategy is not something that can be done in short term or quite easily. If you want to know more about this basic principle and what is going on today, there are different papers already published. One of the main protagonists of all these transformations, Professor Stankiewicz, in the Netherlands at Delft University. They have just an institute on process intensification and process engineering, and a lot of work is done there. And we collaborate sometimes together, by the way. If you are able to do this, the way to try to realize in perspective all these basic principles is to redesign all process engineering, all the industrial process basically, introducing new molecular separation units. Most of the one more traditional today are not consistent at all with the basic principle that we were showing before. Years ago was not important. Today we have to cancel traditional filtration system, traditional process as sedimentation or cyclone, etc., because they are not consistent at all with process intensification principle. And so new molecular separation are important. We have to realize what we call a new catalyst design, not just new catalyst, not just the chemical part, but today what is important is the catalyst design. That means using your catalyst in the most appropriate form to realize the basic aspect of PI. So the catalyst design, which are directly related to the utilization of new kind of reactors, chemical reactors, but we call them today more and more membrane reactors, is another part quite important. We have to design new unit operation for mass energy transfer between different phases. Again, most of the one that we are using today traditionally are not consistent with the basic requirement. So we will see that we will talk about membrane distillation, which is nothing more than normal distillation. But normal distillation today has been realized by creating a big distillation column that you see, this long column in any industrial plant when you visit the plant, and there is evaporation, condensation in thousands of different plates. This is not consistent at all with process intensification. And today people are studying membrane distillation, where exactly the same process, the same equations are valid, but the engineering of the system is no more evaporator condensation through in long column, but is just realizing what is in nature. Our skin is a typical example of a microporous hydrophobic membranes where you evaporate and you condense. You evaporate and you condense. If you transfer this way of doing from nature in membrane distillation, you are a process of distillation much more consistent with the requirement of process intensification. And this is true for crystallization, is true for condensation, etc. Okay? So if you are able to create this new unit operation, basic unit operation, you can have a significant impact in some of the most important problems at the industrial level that we have today. We will have impact in sector as the one of energy. Membranes can be a way to produce energy with methodology consistent with PI. Fuel cell, batteries, and today, new system, less familiar to you as a blue energy. Energy produced by mixing salty water with fresh water. That means pressure, retarded osmosis, reverse electrodialysis, which are all new operations based on the utilization of membrane system. And this will be just these salinity gradients we call also blue energy. And we will discuss a little bit about this. We can try to solve at large, at most, basically, totally, the problem of what we call a water stress. Water, as you know, is becoming a big problem. We need a lot of water, more water. We have a lot of water on Earth, by the way. Water is the most present chemical compound on Earth. But we need better water, better quality, so we have to purify the water. Seawater is not available. We cannot drink seawater. We cannot use seawater in the cooling tower or industrial applications. So we have to produce, we have to purify the existing water. We have to distribute and to organize the water system much better than in the past. That can be done with membrane system, and we will discuss about this. And we have, in general, to rationalize any industrial production by integrated different new unit operation, one of the basic requirements of the process intensification strategy. So this can be quite interesting. And in fact, now if you are looking how to realize all these things, you will see that all membrane technology that we will discuss, reverse osmosis, ultrafiltration, microfiltration, electrodialysis, etc., are all technology that are providing quite interesting opportunities to redesign most part of industrial production in a much better way in terms of cost, environmental impact than the past one. And that is one, and they are becoming much more acceptable, for example, for what concerns the environmental impact. Membrane operations, remember, are not just separations. Traditionally, in the past, membranes were considered a kind of filter, eventually molecular filter. But they are not just filters. They are not just molecular separation, much more than this. They are for sure quite interesting molecular separations, which means about 80% of the cost, operating cost of most part of the industrial production, so very important. But they're not just this. They are also able to realize, improve energy and mass transfer, energy conversion, new biomedical application, etc., etc. Most part of the what we call artificial organs or hybrid organs, artificial liver, pancreas, kidney, today artificial brain, are based on advanced membrane operation, more and more. When you go in an hospital and you visit somebody that is under kidney treatment, for example, or has some problem of lungs, you will see machine where you don't see membranes, but inside this machine, 100% of the operation are normally related to membrane system. The box outside is a normal box, but if you go inside, membranes are just playing the most significant role. And areas as desalination and seawater and brackish water desalination are today already systems in which membrane operation are a dominant technology. Most of you, your parents, if they know something about desalination, etc., they remember that you can have desalination of seawater. And the plants they have been watching years ago were basically distillation system sophisticated distillation, MSF, MMD, etc. These systems are slowly disappearing. Only in few countries, Middle East, they are still big MSF, multi-flash system. All the new plants we will see are basically membrane system. In this area, membranes are already dominant. In a lot of municipal wastewater treatment, we have already new dominant technology we call membrane bioreactors. Here in Korea, we have a lot of know-how and experience in producing new treatment for wastewater at municipal level on many industrial operation. They are all membranes produced and realized in what we call not just separation, but membrane bioreactors. And if you go around the world, big city, if you come to Italy, city as near Venice, that you know, or Brescia or Prato city of 100,000, 200,000, 300,000 people, all the municipal wastewater is going through membrane bioreactors. No more the old traditional biological system. They are not effective under PI strategy. Too big, a lot of space, large footprint, not small footprint, too much energy, not flexible, not easy to control, remote control or automatization at all. So all these systems, also municipal wastewater treatment, are going to be redesigned as systems where separation and chemical conversion are integrated in membrane units. That's why seawater and brackish water desalination, fruit juice, a lot in food, fruit juice concentration, pharmaceutical, gas separation, petrochemical industry, etc., are today basically going to be redesigned, converted, basically using membrane technology. Membranes means to use this kind of system. You can have membrane technology in well realizing the basic aspect of PI, of the system of process intensification. For example, all the membrane operation we have, these are typical membrane module, have a significant lower energy consumption. In some case, you can reduce of a factor, not percent, but factor of 10, one order of magnitude, energy consumption in desalination. That's why reverse osmosis is becoming today very, very dominant technology. You can have much better interaction at molecular level, so you can increase the yield of any process. Footprint, because most part of this plant are much smaller than the traditional one, so you have a reduced equipment size. You can increase the efficiency of the process. You can have a continuous reuse of the raw materials eventually. You can recover and reuse all these components from some of the effluents, what was at the origin of a big problem in terms of environmental effect, is today becoming a way to reuse some of the components present in the waste directly in the process itself. So you minimize environmental impact, you improve the efficiency of the system. And overall, you have a much more friendly environmental operation, much more safe, and much more small in terms of space. You can recognize all these properties typical of membrane technology are the one that I was listing before as a requirement of PI. So at the moment, maybe tomorrow something still better will appear, not easy, because when we are talking about membrane technology, we are talking about something already existing in nature from 50 million years. So we don't know any other system in nature today that able to realize this system, but we never know. Some of you can invent something better. But today, the best way to realize the principle PI are listed here, related to membranes. You will never see membranes if you are not a researcher. If you are not producing membrane in your lab, you will never see membranes, because the membranes will be part of these units, of this module. And what you will have to utilize this module in your process. There are systems, remember, where you will see later, where there are thousands and thousands of these units present in one reverse osmosis plant. There are operations today where in a single plant you have to install something as 3 million square meters of membranes. Huge amount of membranes in a single plant, 3 millions. The amount of polymer we are using in some plants is of the order of 400 tons of polymer to produce the membrane necessary to realize a single reverse osmosis seawater desalination plant. Big amount. Largest plant in the world today are based on membrane operation. Some typical example of already success and confirmation of the hypothesis I was doing today are here. In desalination, reverse osmosis, RO is the acronym for reverse osmosis, is a system which in terms of energy consumption is an efficiency of a factor of 10. So you are reducing for a factor, not percent, of 10, the energy consumption compared to the thermal approach, traditional distillation. In terms of membrane bioreactors, I was mentioning before, municipal wastewater treatment, you have systems which have a factor which are 5 times more compact than the traditional activators large plant. So you reduce the footprint by a factor of 5. In some membrane reactors, chemical conversion, the conversion factor is 5 times higher than traditional reactors for the same reaction. So these are already examples of success of results already obtained in the last few years. Keep in mind that the membrane engineering everything started in the late 60 and 70 of the last century. 1968, 1970, the first RO installation were realized, a small one, and only in the middle of the 80s, that means 20, 25 years ago, some gas separation were offered to the industrial production for the first time, and membrane reactors are just at the end of the past century, around 2000, on 1998, the first large-scale bioreactor were installed, for example. So all the what we are talking is relatively new in terms of 20, 30 years at most. So a lot of work still will be done in the next decades. That's why, and most of the new membranes, new process has to be still realized, by the way. So that is the situation, that the logic, however, of process intensification is the umbrella under which membrane operations are working. So the real strategy is not to realize membrane system, is to realize process intensification. For realizing process intensification, today, what we can utilize is membrane technology. If some of you will be able to satisfy process intensification with the principle we showed before in another way, welcome. And some examples still exist today. There are something that is not membranes, but something different, still able to realize the PI principle. Some market trends, what is happening in real life, and you can see here, for example, in water, the membrane technology is the most interesting, fast-growing technology today. And you have a lot of application in water with some market that before concerned the 2013, that means last year. You can see here we are already talking money in terms of billions of dollars. This is just the cost of the membranes. If you are looking to the cost of the system where membranes are installed, you have to multiply for 10 or 15. So the market of the past years is already of the order of tens of billions of dollars for the system, just in water. And water here means you can see just municipal water treatment, seems to be is just the reverse osmosis and different numbers you can see here. The installed capacity in the past years was already of about 65 million cubic meters per day of water produced. These are interesting numbers because we will recall in the next discussion this number, because if you are producing 65 million of cubic meter of fresh water per day, you have to remember what is happening to all the chemical that you extract from the water. And here you will combine 65 million is water, but on the back there will be about 37 million of waste, of what we call a brine, salts, that are not in the water anymore. And this is becoming a big problem, what is called a brine disposal. When you make desalination, on one side you are producing fresh water, but what about the brine, the salts that don't go through the membranes? And this in the past was not a problem. A small amount you were putting back in the sea or underground, or no, they would distribute on the ground itself. No more possible when you have big numbers like this one. You can destroy, you're producing water, yes, it's nice, but you destroy the environment if you don't take care of the brine disposal. What to do with all the salts that we extract from the sea, for example. And today we have to invent how to utilize at the best this brine. That's a big problem. But if you can see here, this is about all this production. Basically 60% is reverse osmosis already. MSF, traditional thermal system, that was 90%. When I was a student as you, this number here was 0.5%, was nothing, just the first plant. Today is more than 60, and today is already approaching 70%. MSF years ago was 90%, 95% and more. Today is disappearing, is only 26%, and basically only in one country, Saudi Arabia, for different reasons. All the rest, or M&D, is 8%. All the rest are hybrid. When we say hybrid, it's just reverse osmosis eventually with electrodialysis and others. So membranes are just becoming the dominant technology. Other sector, they're less familiar maybe to you, but for example, in the food and beverage industry, membranes are becoming more and more strategic operations in the separation, purification, concentration of most part of the foods and beverages you have on the table today, all around the world. You can see here what is happening and how is this growing in the years, and this is already 2012. But if you're going back here in 2000 or 1980, this value here was approaching zero. And in few years, in 12 years from now, you see the growing, and this growing is still going and probably will be 100% in the short. That means when you drink your orange juice or milk or any produced food, membranes as a part in the transformation process in the production line, more and more. And that is basically, you can see, all around the world, particularly in the United States, in Europe, and also in the Asian country, more and more. For what concerns the market, we saw before these numbers already, and that is the transformation that is expected. Already now, that is, you see that the amount of, this is the seawater reverse osmosis. The seawater reverse osmosis is going up and up today, is approaching 80% basically of the total market in a couple of years from now. These are the expectations, what is going on. And MSF, that years ago was the only system, MSF is basically going to disappear. M&D is still a little bit present, but this system, traditional thermal system, basically will disappear in 2 or 3 years from now. Still, at the university, very often, except in some case, very few classes are given in which people are telling that, be careful, distillation is traditional distillation will disappear. Today everybody is learning about distillation. Very few are learning about membrane system. But in real life, if you go outside from the university, all around Europe, all around the world, in Europe particularly, people don't realize that 80% of the desalination is no more distillation, it's membrane system. So we have to speed up the introduction of this new concept in most part of the university all around the world. That's why if you go today in China, in Korea, in Japan, in Europe, classes on membrane engineering are just sponsored by the local government. European Union is creating a doctorate only on membrane engineering, sponsored by a European level, because we have to speed up to learn much faster than traditional methodologies, because that is what is happening today. A couple of years, 80%. To give you an idea of what is happening, is that here are some of the world's largest seawater reverse osmosis plant installed in the few months ago. This is the third quarter of 2013. This plant is already in operation. 100% operation started in November, if I will remember. This is a plant of more than 500,000 cubic meters of fresh water per day. So these are the largest plant realized last year. These plants are already obsolete. I will show you later that these plants are already old because the new plants are coming already double production, 1 million, not 500,000, 1 million. So this one, this has been installed in Israel a few months ago, and here you can see here, they have quite interesting small, this footprint looks a big number, but it's very small for the size of the production for 500,000. If you want to do the same plant, not with membranes, but MSF, will be 400,000 square meters, 350,000 square meters, much, much bigger than the one that you can realize with membrane. And the same at the cost. The water cost for this kind of units is of the order of 0.58 cents of a dollar for a cubic meter, for 1,000 liters. If you realize how much do you pay for the water you are drinking when you buy in the supermarket, where 1 liter bottle costs you sometimes the same price, or eventually if you buy in the hotel, double price than this. This is the cost for 1,000 liters. That's why big companies today, Coca-Cola, Pepsi, or Nestle, etc., these people, they prefer to produce water today than just orange, etc. They make more money in realizing fresh water through reverse osmosis, etc., than just other production. One time, I don't know if you're familiar that today Coca-Cola is producing fresh water. When you take a plane and they give you a bottle of water on the plane, it's all produced by Coca-Cola. And Nestle, that one time was producing chocolate and candy and milk, today is producing water, because water is becoming more interesting as a product, because these are the costs of production, already 2009. Other plants, same story. That is the second largest plant in the world, is in Algeria. Just started also here, third quarter this last year, and this is what it costs. You can see here, $100 million, a single plant. So when you make this investment, you must be sure that the system is working. And this is again 500,000 capacity, and this is already in operation. If you go in China, not too far from Korea, if you fly in 1 hour, you will see what is happening in China. In China, they are starting to realize not industrial park, as you have in the United States or in Europe, related to electronic technology, say the IT park or biotechnology. They are realizing the industrial membrane park. Chinese are assuming that in the future, membrane technology will be a very powerful core technology covering everything you will see here. And so they realize this is near Nanjing. Nanjing is a very industrialized city. And they are realizing now, 6 months ago, they started the operation with a membrane science and technology industrial park. They have about 60,000 square meters of installation already there, most parts still empty because everything started a few months ago, in which for the future they will concentrate industry, university, research center, working together for realizing everything on membranes. And you will see that, and that will just, will have no enterprise, just venture capital investment, all in this area, and not for doing one process, not desalination, etc. They do everything. They will work on the CO2 problem, capture and storage. They will work on the water problem, in metallurgy, in pharmacy, in food, in petrochemical, electronic industry. So they are assuming that this kind of technology can cover basically all the problem that we have today, that we were discussing process intensification. Quite interesting, we must be careful, we have to do the same, otherwise we will be dependent from what they are realizing this thing. This is in Nanjing, the Yangzhou Membrane Industrial Park. Another one, not yet realized, is under construction in the north of China, in the Gansu province, in a city called Langshu. Langshu is one of the areas that the Chinese government is identified as an interesting one, and they are realizing already number 2, at my knowledge. Maybe there is number 3, number 4, I don't know, but already 2 industrial membrane parks are present, one already in operation, the other one coming very soon. As we said before, the reason for being involved in membrane engineering is that at least some of the most interesting problems that we have today for industrial development can be approached and solved, hopefully, using membrane operation. And these are some of the cases. Now, we have on Earth today 3 major big problems. We have more than this, more than 3, but 3 are the most interesting. As you know, related to the total world population, which has been increasing significantly in the last 50, 60 years, this kind of phenomena, increasing of the population, has produced some problem. One is the fact that everybody is familiar with the water problem. We have just reduced amount of water, purified water, available for the human being, because the number of human beings is so big that we need more fresh water to satisfy them. And the same is a problem of the global warming, which is related, and the same is for energy consumption, which is related. But there is one problem that maybe not everybody is familiar with, and this is number 3, this one, depletion of raw materials. When we are telling that in some part of the world there is no more water, or less water than necessary, we don't know that in the meantime we have in most parts of the world what is a depletion from the soil, from the ground, during the last 100 years, the last century, of all the raw materials present. We are going to have a disappearing of raw materials, minerals and other stuff, of the order of 74%, 78% in some part of the South America, or 72, 76 all around the world in average. So we have a problem related to water stress, but we have a problem related to the disappearing of raw materials from the ground, because we have not been able to understand what was going to happen in terms of industrial development, and so we were not been able to introduce advanced technology to reuse and to give back to the land what we have been using and extracting continuously. So we have this problem, which is becoming a similar problem to the water stress. So we have today 3 big troubles. One is we need more energy. We need more fresh water, but we need also new way to recover raw materials. However, what is interesting that these 3 problems can be only one. Because if you just redesign following the process intensification strategy, you will see that we can solve the 3 problems with one shot. Because when you introduce advanced desalination system, for example, on large scale with big plants, as the one we saw before, 500,000 plant, single plant, you will have on one side what is called brine disposal problem. But the brine disposal problem can be the origin of a solution for this problem, because all the minerals that we have been extracting and utilizing at the end are going to the sea. So instead of crying and talking about brine troubles, we can identify how to extract, how utilize all the salt that we have been using and sending back to the sea. When we have desalination and we have a system to integrate salty water with fresh water, as I was showing before, we can have a new membrane technology utilizing the difference in Gibbs-free energy between the salty solution, seawater, and the fresh solution, river water. And that is what we call a blue energy. The same concept that when we are mixing different salt and we make oxidation and reduction in your battery, instead of just mixing and changing the color, somebody invented to separate oxidation by reduction to move the electrons that you produce and absorb in an external line, and you have light, you have electricity. Same concept here. When you mix salty water and fresh water, don't just mix and you dilute the seawater with fresh water. If you make this dilution by a system in which there is a membrane inside, and these membranes help you to pressurize the one solution, the seawater, for example, that means increasing the volume in a closed volume, in a closed compartment, you will create transformation of the chemical energy difference in Gibbs energy in mechanical energy, and later on, if you have a turbine, in electricity. That means that through desalination, what can be done, that the problem we have today in desalination, which is basically everybody talking how much does it cost. Energy consumption is a very big problem in the big plant. And the problem that is related, what we do with brine disposal. All the millions of tons of brine that we don't know where to put after desalination, in the future will be transformed. The problem of tomorrow will be totally different. The energy consumption will be no more problem because the system of desalination through membranes will be a system will produce energy, blue energy, instead of consuming energy. The problem of brine disposal will disappear because there will be no more brine disposal. There will be mineral production through all the mineral that we discharge in the sea. And eventually, in the future, the water price, the third problem, will be just at the production cost, because the real profit that you will have will be in energy production and the mineral production. And the water you are producing can be distributed as requested by the public. People don't want to pay for the water. No, we are water. Your body water is about 70–75%. If they charge your body, you become nervous. You don't like to this. And people, the public does not upset. Already now we have a problem on this. So that can be one hypothetic future scenario that will be, if we are able to create a new technology in which we can realize energy production, raw material production, combined from desalination. And that is something that is happening. And you will see that in your country, people are already looking to this, exactly to this strategy in some of the projects. In the last years, in Europe, in Korea, in Japan, there have been big multinational and big research program trying to solve initially just the water problem, water stress. Medina, I directed this project for about 5 years in Europe. It was one of the largest integrated membrane operation for fresh water and raw material production was going in Europe. In Korea, there was a Sea-Aero number 1 for 27 to 212, but now we have already Sea-Aero number 2, You will see what is CAERO number 2, exactly reproducing what I was mentioning before. And in Japan, this megaton that were just to realize, we saw before that yesterday in November, big plant started the operation. And the big plant are 500,000 cubic meters of water per day. Today, in Japan, last November, there was already the presentation of the result of megaton, where the size of the plant is not 500,000, is 1 million cubic meters per day. That means the plant we saw starting last November are already obsolete, already old. The technology is giving you the possibility to produce 1 million today. That means 2, 3, 5 million tomorrow probably. Today, in a few months, all the big plants installed are old plants, because this can be the new one available today. Quite interesting, because already this big program here are very much related to the principle of process intensification. You see here that when you are talking about the megaton, pressure retarded osmosis, that means and is part of the process, to produce energy combined with the production of fresh water. And you will see here that CAERO is already working on the technology that will permit not only to produce fresh water on large size, same millions cubic meters per day, but also to produce energy and to produce raw materials for all industrial advanced applications. Medina was a process in which the traditional reverse osmosis, already, as I was mentioning, a dominant technology, was not anymore by itself. Reverse osmosis here is the core of the system for water production, but all the pre-treatment to reverse osmosis and also all the post-treatment to reverse osmosis has been suggested already as membrane technology. So this is a typical example, very well consistent with the process intensification strategy of the integrated of different operations in the same system, all related to the same technology, membrane technology, membrane engineering, where we have microfiltration, ultrafiltration, nanofiltration to pre-treat instead than coagulation, sedimentation, sand filtration, etc., produce the water to go to the RO. But the most important aspect were here, because now still you have relatively low recovery factor. Recovery factor, the amount of water produced from seawater, in normal distillation, MSF, is about 20–30% at most. In reverse osmosis alone is going to be about 50%, 55%, much better than MSF. But we want to make much better than this. We want to have 90%, 95%. You can do it if you just integrate on nanofiltration, concentrate, on the retentate, and RO, membrane distillation, membrane crystallizers. New technology, quite consistent with the logic of PI, process intensification. And if you do this, you can realize what we call roughly zero liquid discharge. At the end, what you are doing, that you are producing the salted water through RO, but you're also producing concentrate solution that can be very high level of brine with a recovery factor that is becoming 93, 94. And that means you minimize also the brine disposal problem in this way by very small amount of brine available. But more than this, if you also have not only membrane distillation, but membrane crystallizers, you can produce crystals. And so you extract, instead of going to underground in the mines to take out minerals, you take all the minerals are present in the sea, you can take out the minerals from here. So you have a mineral raw material production, energy production if you are also introducing this pressure retarded osmosis or reverse electrodialysis, and fresh water. 3 problems in one single system. That's why, if this is true and can happen, we have to learn which technology can do the job. What is membrane distillation? Most of you probably, except the one already attending the course last year, they don't know about membrane distillation. What is membrane crystallizers? What is MBR? MBR here can be a better way than just this membrane technology already to realize a pre-treatment appropriate for RO. And this is something that came at the end of the project. This is a typical example of what can be done. Now, if you go to the other project, this was done in Europe, but here in Megaton, the one in Japan, that ended last November, and now is continuing for big plant realization. If you want to know more, check about Megaton. Most part of the results are available today. You will see huge plant that will change our way of living, because these are plants related to the concept that in the future we will have huge city, as Seoul already, but bigger than this. Today we have 3, 4 mega cities around the world. In few years we will have about 50, 60 megalopolis, city of 30 million people, 25 million people living together, which means all the system for water distribution and has to change completely in this logic. That can be done using this kind of approach. You can find data, I will show you some of them. But interesting here already, when Megaton started, the concept that you can produce energy, osmotic power generation, combined with desalination was already present. Very important one. If you go, and that's been already related to the realization of huge plant, which means that the reliability, the trust that the engineers and people have in this investment is very high. When you realize plants that cost you billions of dollars, single plant, it means that you know that can be done. Otherwise, you don't take any risk of this size. And that was already, this plant was optimized for 1 million cubic meter class plant, all standardized plant of this size. And it can be bigger than this in the future. And there will be also some other innovative way to produce energy and eventually minerals that are coming from the same concept. You can see here the all industrial world in Japan were involved in this project, not only one, but from Toray, Hitachi, Toshiba, Mitsubishi, etc., they are all involved in this kind of story. But if you go to Korea, that is familiar to you, you know what I'm talking about. Maybe you're not aware that here in Korea, they started, roughly in the same year, a very similar program to Megaton and to Medina, by the way. We were working, networking all around the world. I was a part of the Megaton, for example, in the advisory scientific council. I was sitting there, and very well related to this plant, this process also. Similar final objective, big plan. They are not talking here about the 1 millions, but they are talking about the largest single truck, about this 37 cubic meter per day single units. If you multiply these units for 10, 15, you have the 1 millionth production that we were talking before. So very similar approach. And that's for contribution to humanity, et cetera, et cetera. So big project, a lot of money. This process was about $200 million for 2 or 3 years invested. But what is happening today is quite interesting. By the way, this has been quite successful. During the process, they were introducing some new concept, forward osmosis combined with reverse osmosis, and we will discuss what is forward osmosis, what is reverse osmosis, and that was some innovation coming across the study. But if you go to see the end of the story, the concept, first of all, of this hybrid desalination process for energy resource recovery, not for this producing water, but for energy and resource recovery, became part of the vision and the concept of the OCW-HYU program. And now that they are developing more in terms of research, in the next step, you will see here that membrane distillation and membrane crystallization for RO brine production is a part of the OCW number 2, where about $70 million are going to be invested. So the same concept I was telling before, that we were assuming a little bit romantic and not easy to realize because too many transformation in one. Here they are. They will be the work that some of you, when you will be out from the university, will have to carry on at industrial level, because that's what in Korea the CRO in the research center structure, this is the point. Extraction of valuable resource from RO brine. Instead of talking about brine disposal, they are talking how to utilize the brine at the best using this kind of technology, the one that we will discuss here, and energy, etc., etc. Reverse electrodialysis and this pressure retarded osmosis as basically part of the desalination. So desalination is no more just desalination to produce more water and to sell bottle of mineral water at high cost. It's the way to produce minerals, to produce energy, and eventually also water. But water is becoming the less really interesting aspect. Just to show here that now you have C-hero number 2, and C-hero number 2 is subdivided in all these aspects I was mentioning before. You have already PRO hybrid, you have RO for osmosis hybrid, you have valuable metal recovery, project number 1 already in progress, and you have production and different other aspects of this. It's not just the mineral, but you can have also building material and hybrid system. And what is interesting for you is that that is the same kind of logic. Also, you have membrane distillation combined with PRO. We will discuss about these things because you can see in C-hero, this concept is very well designed, very well present for reducing the brine, for the recovery of energy from the recovery of resource. So this is a strange slide telling that we can, instead of, don't forget about water, energy and raw material, is C-hero now. It's just becoming a very interesting aspect C-hero. And here it is, the same number. What is interesting for you is that this number 1 already working from 13, from yesterday until 18, 5 years, with 26 billions of Korean won. And the number 2, I think, is now starting now. This one is already running. This one is starting. And this is again for osmosis RO. And this will be again starting this year, 14, 19, 32 billions. So about $70 million, billions of yuan, totally devoted, as you can see, not just to water production. Well, the same plan that we were calling for water production, but now it's no more water production, is energy and raw materials. Exactly as we were discussing before. That's quite interesting and will help. Because, so what is happening here, I was mentioning that we are producing today with the existing plant, not the 1 million or half a million. This was the previous one. Already 65 million cubic meters per day. Now, if you calculate this one, realize that on the back, we are also producing 37 million of cubic meters of brine, of minerals. People were not looking to this. They were just crying, and if the environmentalists were not around, they were just putting back in the sea, forbidden by law already today, and more will be impossible to do these kind of things. So how to do with it? What to do with this? This is the most interesting part of the story. Forget about the water, because now from the RO brine, we can do different things. First, we can still produce water from the brine by membrane distillation and membrane crystallization. But from the same brine, using membrane crystallization, we can extract minerals. And we will see minerals much easier and a better way because this brine is very clean. It's very well pre-treated for going to RO. So it's not the kind of brine that is in solar pond, etc. Very different, but quite interesting. You can have a polymorph with special habits in this way. And by PRO and R&D, you can produce energy. From this amount of brine that was considered a trouble, now is the origin of water production, raw material production, and energy production. And that is exactly the concept, no more Medina, no more C-hero, no more megaton, C-hero, that means your country, that is investing 70 billions of yuan in the next 4 or 5 years to realize exactly this kind of logic. We will discuss, to understand better, what is this blue energy that we can utilize. And you will see that will be this amount of energy that we are consuming in the same years that I was showing before is increasing exponentially because not only water was increased in this way, but energy. Now, this energy, we need a new source of energy, competing with nuclear energy, by the way. And this blue energy is the energy that we can have when we mix together salty water, seawater, or concentrate seawater, eventually through membrane distillation, with fresh water. The difference in Gibbs free energy of the salty solution with the fresh solution, when they are mixed together in the appropriate way, using a membranes in between, will produce significant amount of energy. About 20% of future energy can be coming from salinity gradient. Today, basically zero. We have 3 osmotic power stations already running in Norway, in Europe, in Netherlands, and one in Oman, in the Middle East. Small one, but running in showing the potentiality of the 2 systems, reverse-electric dialysis that we will discuss, and pressure-retarded osmosis that is very similar. Interesting just to remember, we will discuss again, but if you enter in this logic to have membrane crystallizer on the concentrate of RO, so from RO on one side you go out with fresh water, and all the concentrate brine disposal is becoming a membrane crystallizer. And if you do this and you look what is today in the water, you can, from what concerns magnesium, magnesium is a strategic element already now extract basically from seawater. In China, all the magnesium is coming from seawater, basically the same as in Israel, where there is from the Dead Sea. You can double, if you now take this amount of salts present in the brine already existing today, you can extract basically this number, tons per day, and you double the production of magnesium on Earth just using the magnesium present in the brine produced by the RO plant today. With lithium, which is becoming one of the strategic elements for the future related to the lithium battery and similar, you can increase about 30% of the production of lithium just by extracting the lithium from the brine that we have today. So quite interesting if you can do this. And so you will have at the end that in your system you can have the energy and production. This slide is just showing you that the system for energy production, by the way, is not just on the seawater. There are some hypotheses to produce blue energy also using as a feed water biological system. And Yamamoto, the inventor of MBR, is just suggesting that don't look only to seawater, but any other feed water can be utilized from the same basic concept to produce blue energy on one side and to produce brine on the other one. If you speak with philosophers of old tradition, not membrane people, not engineers, but people who are working on the modern, late modern, postmodern age to the sustainable world for the next 10 billions on Earth, what is coming out is a guy called Professor Tambo, and Professor Tambo is a very well famous professor in Japan, and he was talking about the water district, and this means how we have to redesign all the water system worldwide in front of what is transformation, is a big city of 20, 30 million people, and different consideration about the ergonomic system than better than the ecological one, etc. But for our interest, membrane technology, reuse and desalination are key to establish the system for the future. More than this, when you're just discussing more in the postmodern period, that means the last 100, 200, 300 years, where he is talking about all the problem of the water quality and the amount of energy necessary and how to protect the diversity of the system. So conclusion, various membrane technology is a key to make up postmodern urban water metabolic system, how to treat all the municipal and wastewater treatment in the logic of the postmodern period. That was very surprising, interesting for us, for membrane people, because we were not expecting such a strong statement from people who don't know too much about membranes, but they, when they are now analyzing the system, they are, that is the way of doing. And that is what they expect in the term of the new operation that will be done, related to the problem of desalination also from not only desalination of seawater I was mentioning, but also in some other situation as the one of the municipal wastewater treatment. And that is some of the example that all these people in Tokyo were giving. And also interesting here, that's why, by the way, this is not only in Japan, this is what is happening in China. China, they don't have a very well organized system as a Japanese or Korean, so they don't have yet a national program, no CIERO, no Megaton, no Medina for the moment. However, they are analyzing the system exactly in the same way. That means through desalination, they are no more looking to desalination only for producing water. Desalination for them is a way to produce electricity, to control electrochemical, petrochemical world, and to go to working about concentration, drying problems, and all the chlorosoda plant will be going through this kind of system. So basically, again, desalination on one side is involved in the fresh water production, but on the other side is involved in many other basic problems, from aquaculture to brine purification in this system for water production, for sodium chloride production, etc. Same concept also in China, starting now. Not well organized as in other countries, but the same story. Okay, this is what we were considering already. Keep in mind that when you realize, for example, one of these blue energy process, pressure retarded osmosis, just to clarify that this is a system that this is again related to this Tanioka, but he was talking together with Tambo. These are systems that are becoming very flexible systems that are changing completely our way of living, because you can have a system for the treatment of and producing fresh water combined with the pre-treatment, combined with water, with energy production, combined with, again, both of them are energy production. So this system is becoming something that will change completely also the architecture and the scenario of our city in the future, if these things will be realized. Some of the numbers, again, to justify what we are talking, the power density that you can realize with pressure retarded osmosis is already now, at the end in November of last year, of the order of about 21 watts per square meters. If this number will be real at industrial scale, blue energy will become very popular shortly. Today, most part of the people, we are working in reverse electrodialysis, we are producing 4, 5, at most 8 watts per square meters with the existing membranes, with the existing technology. Japanese are already coming, and they are offering, with one of their plant, this kind of hollow fibers, 21 watts per square meters. Nobody is investing in huge plant on this number because we don't know, but some people are telling that they have the fibers for doing this kind of things. If this will become real, a lot of problem will be solved. We will not discuss too much about membrane production. Professor Yonmo Lee will discuss about membrane production after the middle term. However, it's interesting I'd like to mention already now that most of the membranes available today are not yet appropriate for doing what we are discussing now. Because, for example, if you want to realize CIERO, you need new materials, because CIERO is assuming that you have to realize membranes, not only the hydrophilic one that you are using in reverse forward osmosis or for reverse osmosis. You have to realize membrane distillation, membrane crystallizer, eventually membrane condenser. In this case, you need membrane very, very different from the one for reverse osmosis. You need hydrophobic microporous materials. and you will learn what that means in MD, etc. Very different than reverse osmosis. Same process eventually to produce fresh water, but totally different kind of membrane, transport phenomena, problem you have. So you have to open the world for membrane fabrication to new, not only to polyamide or to traditional cellular acetate materials, but also to some material of this kind. And not only the traditional one as PVDF or Teflon or this polytetrafluoroethylene, but new materials are today for the first time under analysis to become part of this millions and billions of dollars market that we showed before, as ALAR, as iFlon, etc. Polymer that very unknown to most part of us, of you for sure, and this will be one of the areas where people will work a lot. Until now, we have been talking of this integrated membrane system related to water, and we will discuss a lot to justify your necessity to learn about RO, etc. But keep in mind that not only water. This is the case of biofuel production. Biofuel production, which is one of the other area of big interest, from biomass to arrive to some biofuel, not just hydrogen, but also some liquid hydrocarbons, which is a way to solve the problem of the storage of hydrogen. Hydrogen, no, you produce, but if you don't use immediately, you don't know how to store the hydrogen. You can produce from biomass some biofuel, which can be just a liquid hydrocarbon, so you solve the problem of storage of hydrogen, much less dangerous. Also, the production of biofuel is suggested today as a nice integrated membrane operation, where you're going to use submerged MBR, membrane bioreactors, in most part of these steps, and all the downstream will be just membrane bioreactors, will be just nanofiltration, reverse osmosis, membrane contactors, and also the final formulation of these products is going to be through membrane emulsifier, etc. So this is another case in which basically all the production of biofuel from biomass, and that can be from algae, can be from corn, what it is, at the end can be an interesting example, totally new today because this is not existing yet, of an integrated membrane operation, exactly as the one that we saw in Sierra, but not for producing fresh water and mineral, for producing energy and new products as a side product. So the same logic, the same final goal, but in totally different field. In the petrochemical industry, basically, instead in the water industry. So that's also interesting. And that's another case, again, in petrochemical industry, where the ethylene plant, ethylene is product number one in the petrochemical industry. Ethylene can be produced in the future, again, to an integrated membrane operation, starting not from cracking, by the way, but from a membrane reactor from gas for the production of ethylene, and all the different steps, downstream process, separation of the elimination of the CO, or separation of hydrogen, from ethylene, ethane separation, and again, some water purification, all these things. You can see here for having on one side pure hydrogen, on the other one just the specific hydrocarbon necessary, etc., propane, propane, everything is membrane. And the people producing this, some is us, but these are the people, this name here, some of you know where it is. Anyway, one of these names are the people producing the plant today, huge plant in the world, not just professor, but the one that are going to produce and to realize big plant are now working, not for tomorrow afternoon, but for the future, exactly on this line. So water, biofuel, ethylene, etc., are becoming some here. And this is, we have no time, we will discuss later on, but for doing this, we have to learn not only on traditional membrane operation, but also we have to learn about membrane distillation, membrane crystallization, membrane emulsification, and you will see also membrane condenser. That is a new process coming now. If you go in literature, you will find one paper, two papers eventually soon, on new process operation, all consistent with the logic that we have been discussing before, process intensification. Just the case of membrane distillation, distillation is one of the oldest understood operation that people realized long time back. You can find evidence of the small desalination 2,000 years ago. People were already writing and designing some of these things, in which we have what is called natural hydrologic cycle. That means we can have water. The water evaporates normally. It creates a cloud, etc. From cloud you have raining, going back, underwater, etc. This is a natural cycle. Keep in mind that if you analyze, and you are here, and you are drinking some of this water or using this water, if you mark this water, the same water will come back to you here in about 10, 15, 20 years. So the reuse of water has always been present on Earth. Long term, 15, 20 years of time before you can use again the same water you have been using today. In the years, people realized how to make this kind of phenomena useful for industrial application, and so you made thermal distillation, warming up a little bit, not using the sun, but warming up here, and so you realize this typical distillation system. And the engineering has been very sophisticated, and the years has been realized typical distillation column. Instead of just using a boiler, etc., you have a complicated, sophisticated way to separate different components with much lower energy consumption, etc. Today, these things is 100% not consistent with with PI strategy, not at all. In terms of footprint, energy consumption to separate the salt from water, etc., etc. But exactly the same kind of concept can be realized in a much better way, consistent with all the principle of PI, small footprint, much less energy consumption, factor of 10, remember, in this way. You can take not thousands of these different evaporation condensation steps, but you can use billions of pores in hydrophobic membranes. On one side, you will have your seawater. That was actually what was entering here. And the seawater cannot penetrate in your membranes because it's hydrophobic. But when there is a pore, you will have evaporation. If there's empty a gas phase, so some molecules, not only the volatile, not the non-volatile, but only the volatile water, if it's seawater, will evaporate here. And if you apply a small delta T to 5 degrees, this is a very porous system. 80% of these membranes is empty, so you can easily move vapor across and recondense on the other side. So instead of realizing distillation with this engineering, which is not consistent with PI, you can realize distillation with this new engineering, which is very, very consistent with PI. And that's what we learn from nature, because these membranes is our hydrophobic microporous system, it is our skin. So engineers have been learning and realizing this way. This is quite interesting, and that is one of the processes where more and more, including if you go on the 10th floor here, people are working to improve membranes, engineering of this kind of way to make something that has been always done in the last 2,000 years and more. So that's a typical example of what we mean for new unit operation today. How to realize the same basic concept, the same basic idea already present, but with an engineering much more appropriate in the logic of PI. The same story is when you are talking about crystallization. If you know how to handle the membrane distillation, you will realize that you can concentrate your feed at very high value. There's no, as in reverse osmosis, dramatic flux decline. You can there is no concentration polarization effect controlling the interfacial phenomena. So you can concentrate and to realize a supersaturated solution on this side with no flux decay that make system not possible. And if you do this, this can be an interesting way to realize, and you can also separate eventually the crystals continuously when you form in such a way that you don't plug all your membranes, and you can realize quite interesting system, and you understand, if you do this, you learn something. You learn that it's not just an evaporation here, it's much more than this. You evaporate for sure, but also the influence of the chemistry of the polymer you are using on the activation energy of the process is very important. You can change completely the kinetic, the activation energy, moving from Teflon to acrylonitrile to PVDF, etc. So this is not just an evaporator, it's a crystallizer with properties much better than any normal crystallizer, in which this kind of effect is not present at all. So if you understand this, you can produce interesting crystal for protein, from salt, etc., and you can also realize selective polymorph crystallization. That's why you have to learn about membrane crystallizer, because it's one of the technologies that is just changing traditional unit. Crystallization is one of the most important basic unit operation in process engineering. But now it's going to change significantly. And if you go on the Journal of Crystal Growth and Design of the American Chemical Society, you will find the front cover of the couple of issues devoted to this new kind of way to crystallize everything. So quite interesting. And you can also realize membrane emulsifier, the same logic, with using hydrophobic or hydrophilic membrane, and using this pore size distribution to realize a very uniform monodisperse emulsion. Emulsion is the second final formulation of most part of the process in, that we have today. When you produce something, how you can have the final form of your production, crystals or emulsion. When you are using your shampoo in the morning, or you give some food to the children, etc., they are emulsion. To produce emulsion is quite important, and today membranes are also controlling the way to produce emulsion, etc., etc. The last case I would like to mention, and if you will time we will discuss, which is not until now realized at any industrial level, so it's just a new area of research. We were talking before about a membrane distillation. That means if you warm up on one side of your membranes, some liquid is going in vapor phase, moving across and condense on the other side. If you are a smart chemical engineer and you know about the problem of condensation, gases in liquid, just the opposite, instead of warming up, you can cool down. You can decrease the temperature, the interface. So if you make your right calculation, you can condense. If you have a supersaturated flue gases going in the sky, and you have many around, you can try to extract, to condense the liquid, the water, for example, cooling down on a hydrophobic microporous membranes. And that is what we call a membrane condenser. You have a retentate liquid and you have permeate gas. And that can be quite interesting, because as in crystallization, you are learning at the end that not only you make the separation, and you have to decide how to make it, etc., but you can also increase significantly the quality of this of the condensation. Let's see if I have a slide here. We'll see again later on, but you can see here, introducing some new parameter compared to traditional condenser, you can, that means for changing the feed velocity on the membrane surface, you can condense your water, but you can change the level of contaminants that will be dissolved in the water that you are going to condense. Here is ammonia or fluoridic acid, SO2, etc., etc. And this is impossible with traditional condenser, and this is the case of the SO2. You can see here, this is a theoretical prediction, the amount for different level of water you can recover, that's the amount of SO2 which are present. These are experimental results. So you can change in the parameters controlling the condensation. You can decide which, not only to produce the water, but to produce water with a certain level of contaminants, can be SO2, can be ammonia, can be fluoridic acid, can be what it is, and in one step you take two birds. You condense the water, but you change the level of contaminants present. Quite interesting and quite useful for different operation. Okay? We can stop now. There is some more example of what membranes are doing, but I think the intention was to justify why, for the next couple of months, we will discuss about membrane operation. because what you saw, this membrane operation can be quite interesting. The existing one are already running large scale, and in your country, people will invest. You will pay tax for making a real membrane distillation, membrane crystallization to extract the minerals, to produce energy, and to produce fresh water. But in the future, more than this can be done. New technologies are coming, so we have to learn what can be done more on the same line to realize what has been done already and to just develop the new one. A typical case, I don't know if we have time we will discuss, is the produced water. How many of you know what means produced water? Who knows about produced water? Nobody. This will be the biggest problem of the future. Produced water is all the water related to the oil extraction. And you know, oil still will be, for many years from now, one of the big problems, one of the source of energy. Now, when you extract oil from underground, already now, for 1 barrel of oil you extract, you have to use 7 barrels of water, because we have what is called, no, you have to push. The oil is underground. One time, long time ago, the oil was appearing as a kind of lake on the surface, no more. Now the oil is down, and it's very difficult to take it out. It's becoming more viscous, deeper and deeper underground. So we have what is called enhanced oil recovery. You have to push water or to push CO2 underground to move this oil up. This is done with CO2 or with water, basically with water. This water now is becoming a critical problem, because in some country, Kuwait, for example, Canada, and more everybody in the future, the amount of water you are going to use to extract oil is becoming more than the amount of water you can use for agriculture or industrial production. So this water you have to find a way to reuse as much as possible. And this is a problem that years ago nobody was aware. Now this term, produced water, is becoming more and more popular. If you go on the web, click produced water, you will find a lot of work. And now that, you know, in the future people are assuming that they will extract shale gas in the United States of America or all around Europe. This shale gas is still a bigger problem. Shale gas is the gas that is entrapped in the fractures in the rocks, etc. Very difficult. You have to push more. So more water, more gas. So this is becoming bigger and bigger. So we have to find how to solve this problem, to reuse continuously the produced water in the field, offshore, offshore and onshore, etc. Membranes will be the way to solve. So there will be new polymer, the one I was mentioned also before, just developed and just studied for this kind of application. So this is another case that we will discuss as typical example, and produced water is becoming an area where new membranes are also necessary. The existing one don't do the job. We want, no, the membrane plant we were discussing before. Keep in mind, some people were assuming that membranes, yes, but they are not resistant with the years, etc. Not at all. The membranes, if you learn, if you have a good membrane engineer who know how to handle, who know how to pre-treat, the lifetime of your membranes in real life can be of the order of 11 years. In the past, they were giving for 1 year, 3 years. Now that we know, people have been working, you can have guarantee for 11 years of operation, which means you have to change the pumps, you have to change the tubes, the valve, the operators sometimes, but you don't change the membranes. The membranes are there. For this application, this problem is different. Today, we don't have membrane that can stay for 1 year. So people have to work more in this department, Anyang. There are people working also with traditional polymers as PVDF, but try to understand better how to realize membranes that can stay a long time and related to their own polymer we are using, etc., how to blend this. So a lot of work has to be done, particularly for the new operation, as the case of produced water, and similar, that means ultra-pure water for the electronic industry, etc., etc. And new solvents will be produced, new membranes has to be produced, etc., with some different morphology than the traditional one, if you want to have better process running related to the, you will learn that the pore size is very important to realize membrane distillation, membrane crystallizer, for example. Less important in reverse osmosis and similar. Okay, we can stop here. We will meet again on Friday, and we will start, well, maybe close this, and we will start to speak now one by one of the different processes that we have been realizing can be important for our future energy, water, raw materials, and a lot of industrial application. Microfiltration, reverse osmosis, etc. Looking not only to the materials, but looking to the transport phenomena controlling the separation. And what is more important, you will learn that not only membranes are important, but everything that happens on the membrane surface in the bulk of the solution can kill your process if you don't understand what is going on. That means concentration polarization, thermal polarization, fouling phenomena, biofouling are quite important. You can have an ideal membrane that does not work if you don't keep control of these parameters, which is not related to the morphology of the membrane, but what happens in the interface. So both things have to be done. Okay? If you have any problems, some of you are familiar, so you can talk, but the ones who are not familiar, you can ask and send messages to my email or to Ji-Hoon that you saw before, and you will receive on your email copy of all these slides, and so this material is available. If you want to have more and for some reference already there, if there's some other reference that you don't find, ask me, and you will receive on the email everything is necessary. Okay? So we meet Friday morning. Thank you.